class, welcome to the first video of the second part of Chapter 4. Alright, in this next section we start to examine rational functions. Alright, and basically we need to understand, and hopefully we know this already, ratio means fraction. So if we kind of put 2 and 2 together, we fraction, rational functions. Okay, a rational function is a function in the form r of x, or it doesn't matter, you can use f of x. But what I really care about is that it is p of x, let me rewrite that. P of x over q of x. And what do I mean by this? I mean I have a fraction. I have a polynomial in the top, I have a polynomial in the bottom. And when that is the case, we have a rational function. Now, it's also super important, it's not okay for q of x to be 0. So we say q of x is not the 0 polynomial. Now, we already looked at some of these actually. I believe it was back at the start of Chapter 2 when I gave you that full sheet of different types of functions and their graphs. We already looked at this one, 1 over x. Hopefully you guys remember. We call this the reciprocal function. And if you remember, there are some asymptotes. Alright, we know, and actually let's think about it like this. We know that if we plug in a 1, so if I plug in x is equal to 1, 1 divided by 1 is 1. Alright, so I can get that point. I know that I can plug in -1, and I would get this point down here. Can I plug in 0? Like, can I plug in x equals 0 right here? No, that is not okay. You cannot divide by 0. So what really is happening is you are finding... Did I lose my ruler? Sorry about this, guys. Yeah, we have an asymptote. Alright. It's hard to see. Maybe just do it by hand. Alright, we have a vertical asymptote, which is good. And if you remember, we also have a horizontal asymptote at 0. And what we are going to do when we have this reciprocal function, or what you should be doing, is you should get as close to that asymptote as possible. So something like that, something like that, and then we can do it something like this, get real close, something like that. Okay, you want to get as close as possible. It doesn't have to be perfect, but understand what's happening. Now what I want you to notice here, this x, it has a degree of 1, or it's odd. Okay, so when you have an odd degree, it's going to go, or it's going to approach infinity at opposite ends. And hopefully I will drive home this fact on the next picture, or the next graph, because now when I look at h of x in example 2, I no longer just have 1 over x, I have 1 over x squared. Alright, so same type of thing. Can I plug in a 0 for x? No. I'm still going to have a vertical asymptote at 0. I'm still going to have a horizontal asymptote at y equals 0. The thing that you have to be careful of, though, is what happens when I plug in points. If I plug in 1, well, 1 squared is 1, so 1 divided by 1 is 1. When I plug in -1, -1 squared is positive 1, positive 1. 1 divided by positive 1 is 1. So what's happening here is it's all staying above the x-axis, kind of like that. And this is what I meant in my note on the other one. You see how the degree right here was a 1, or it was odd? Well, that means that on opposite sides of the vertical asymptote, one approached to the bottom and one from the top, or negative infinity, positive infinity. Whereas now over here, my degree was even. And what do we say? I'm going to say same ends. Alright, the same ends. So even degree, same ends, odd degree, opposite ends. We'll practice more of that when the time comes. Now, we need to remember some of our domain work from earlier in the year. This should be hopefully very easy. We remember what? And this is going to be the case for most of these rational functions. We're going to have to worry about the denominator, right? The denominator cannot equal 0. This should be review. So when I look at this, I don't necessarily care about the top right now. All I really care about is that this x plus 5 in the denominator means that I cannot equal 0, or x cannot equal negative 5. So you can write that in a couple of ways. You can go all reals, but x cannot equal negative 5. You could also, and I know it's a little harder without a number line, but you could go from negative infinity to negative 5, and then from negative 5 to infinity. I would say this is more of the calculus approach. Alright. But either of these answers will work very nicely. Okay, what about this next one? R of x, 1 over x squared minus 4. Okay, we're not ready to work with this yet. I would say, let's factor. X minus 2, x plus 2. Now this is nice. Now I can just immediately say, well, I know that this factor can't equal 0. I know that this factor can't equal 0. So again, we are in an all real number situation, except x cannot equal plus and minus 2. And we can see that because of the factored form. If we move on to the next one, we see an x squared plus 1 in the denominator. When we try to factor it, we say there are no real solutions, right? There's no real solutions to x squared plus 1. So if there are no real solutions, are there any restrictions? Nope. All real numbers. Alright, moving right along to D. This is rational because there is a non-zero polynomial in the denominator. But is there anything to really set equal? Is there a problem to set, not equal to 0? No. We already know that 3 cannot equal 0, or 3 does not equal 0. So in this case, there's really not a problem to set, and we just say all real numbers. Alright, E and F. This is where I want to do some talking here. You need to be on the lookout, because I hope you're okay with me rewriting the numerator like that. And what I want you to notice here is, what do you see in both the top and the bottom? Well, I see an x minus 1. So of course, cross cross, and we get x plus 1. Here's the problem though, and if you remember back from our work with domain back in chapter 2, domain, any restrictions occur anywhere in the problem. So even though I don't see a restriction at the end, I have a restriction at the beginning. Okay, you have to look for restrictions throughout. So this, I would say, is all real numbers, but x cannot equal 1. Let's box that one. Okay. When I look at F, these are the same thing, right? X plus 1, x plus 1. Did this have a restriction in the domain, in the denominator? Absolutely not. So this one is just all real numbers. Alright, so there's a big difference between these two. Even though the functions are going to look very similar, very, very similar when you graph them, there's a restriction. Okay, and so what we are going to learn about, and hopefully maybe you guys already learned about this in Algebra 2, is that E, let me slide down here, E has a hole in it. E has a hole in it. Alright, and what we need to know is that holes are always going to appear when factors cancel. Alright, that's what I meant by x minus 1 and x minus 1 in top and bottom. They canceled out. Anytime that occurs, you are going to get a hole in your graph. Now to get the y value, you get the y value by plugging x into the new function. All right, so what I would have to do here is I would have to say, well, I know there's going to be a hole at 1, right? That's what I found. But if I plug 1 in, 1 plus 1 is 2. So here I know that the hole is at 1, comma 2. Okay? That's what we're looking for. That is what we're looking for. And again, this is just kind of, we're throwing a lot at you here in the first video just to kind of learn some stuff. All right, now, next thing we're going to do is we're going to examine some graphs. We're going to get real good with domain, range, and asymptotes and whatnot. Okay, so maybe if you have a ruler, that would be good to use if I can pick mine up. Okay, I got it. All right, so first thing you're going to want to do, and the graphs aren't the best just because the software we used, it really darkens the lines, but you can kind of see that there is a vertical asymptote right there at x equals 2. Sorry, I'm a little bit off. Let's see there. That's a little better. Okay? And I also can see that I have a horizontal asymptote right about there. All right? Now again, the lines are just super fat, but hopefully you guys see it's going down, 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 down forever, and then up forever from the right side as it approaches x equals 2. So those are my asymptotes, and now I need to kind of figure out some things about domain, range, and equations. So domain, nothing changes. This is my x's, right? I know that I'm starting at negative infinity, and I'm coming all the way over, but then what happens when I get to x equals 2? It will never equal x equals 2, sorry. So I know that I need to go from negative infinity to positive 2, and then I need to go on the opposite side too, right? Because it starts right back up. So from 2 to infinity. What would I say for range? Well, the range starts down and it goes up forever, ever, until right here at y equals 1. So negative infinity to 1. And then it picks right back up on the other side and goes up forever. So 1 to infinity. Now horizontal asymptote, please just remember hoi. So you know horizontal lines will be y equals, and y equals 1. Kind of oppositely or conversely, vertical, vux, so you know x equals, and whatever that vertical line was, it was at x equals 2. Now the last one, oblique, some people call it the slant asymptote instead. I sometimes do. So if I ever say slant asymptote, I mean oblique asymptote. And really what I mean is there some sort of line diagonal, all right? And in this case, in this picture, I would hope we can agree there isn't one. There's no diagonal line that nothing is touching. So here I would just say none. You don't have to put quotations, but I want you to know that you should answer it with a none or like a dash or something. Like give me an answer. Don't just leave it blank. All right? Now, as we move on to the next one, it looks as if I have a vertical asymptote right here. It looks like I have a horizontal asymptote right here. Oops, sorry. And now we're ready to answer some questions. So, domain. Domain is going to start at negative infinity. And because I have a vertical asymptote at negative 3, I know that I have to stop at negative 3 and then start right back up at negative 3 because it will never, ever actually have an x value of negative 3. All right. Now range is a little different on this one. This is all above the x-axis. So what am I going to have to say here? I have nothing until here, and then I go up forever. So it's 0 to infinity, and just be careful. Remember, is it ever going to actually hit 0? No. So we have to use a parenthesis, not a bracket. All right. Ooh, this one. This is going to introduce one of those new concepts, I think. So, sticking with my theme of horizontal and blue, I think we would say that we have a horizontal asymptote right here. Sorry, vertical asymptote, my bad. Vertical asymptote right there. And let's go with red again, just for right now. Okay. Maybe something like that. Perfect. Okay. Again, I know the lines are kind of fat of my actual graph, but what I want you to know is that this is getting really, 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 really close to that line that I just drew in. And let's think about this domain. I know my graph is over here forever, ever, until this spot, right? It goes up forever, and then it never actually hits x equals 0. So I need to say from negative infinity to 0, but then it picks up right again on the other side, so 0 to infinity. For the range, is there ever a y value that it's not going to equal? No, it looks like I always have a graph somewhere. So here, I could go negative infinity to infinity. This one's nice. It's asking for the intercepts, just to kind of introduce. You guys know this. Y-intercepts, hopefully we agree there are no y-intercepts because it can never equal x's, or x can never be equal 0, so it can never be right on the y-axis. But it does hit the x-axis right here and right here. So we can say plus or minus 1, 0. And now the asymptotes. Okay. So, horizontal asymptotes. None. Right? There's no horizontal asymptote anywhere drawn in. Vertical asymptote. Oh yeah. X equals 0. And again, that's a Vux situation, so x equals 0. Now, this oblique asymptote, or slant, this is where you need to use y equals mx plus b. It's still a line, right? It's still a line, so we have to use a linear equation or linear function. And so we just examine and we see, let's see, y equals, my slope here looks to be going up 1 over 1, up 1 over 1, up 1 over 1, okay? So my slope is 1. I put my x, and then the b value. Ooh, y-intercept of this line is 0. So plus 0, which means I can just say y equals x as my oblique asymptote. Alright, almost done. Almost done. We're going to do a few more, I'd say slightly trickier and good to talk about. What do you notice about this top picture? Hopefully you agree with me. There's just more pieces, right? The other graphs that we did, there were 2 pieces. Now we have 3 pieces, and that is fine. Alright, we're still going to find our vertical asymptotes. So something like that. Is there another? It sure is. There's another one right here. So I draw another one. I have a horizontal asymptote, so I draw it in. I don't have any slant asymptotes or oblique asymptotes, so I'm ready to go. Horizontal asymptote, or asymptotes. Didn't we say there's 2 of them? There's one at negative 2. So we have one at x equals negative 2. And we have another one at positive 2. Alright, so 2. Oh my gosh, Guys, I'm so sorry. Ugh. I'm just out of sorts this morning. Okay, my bad. Vertical asymptotes, x equals negative 2 and x equals 2. Horizontal asymptote, a horizontal line, because I know that horizontal is side to side, left to right, is y equals 0. Extremely sorry about that, guys. I am sorry. And then, of course, oblique, what do we say? None. Do not leave it blank. Say something. Say something. Okay, I can do this. I'm almost done. All right. So for this last graph, it's a little bit more spread out. It might be a little tougher to see some things. So what I want you to understand is, for vertical asymptotes, like we know that we have to go somewhere on the left side of this line, so maybe like right here. And the only thing I would say is make sure that you also kind of test from the right or from the other side as well. So like if you know it can't cross a vertical asymptote, then I can't put one right here because that means that this graph right here crossed it. So hopefully, with that in mind, combining both ideas, both from the left and from the right side, we can see that we have a vertical asymptote right here. Alright, and when we do that same thing over here, this one's looking a little easier. I would say it's just right there. Alright, so there are our vertical asymptotes. Let's see. Horizontal asymptote. This is going to be my little wildcard moment of the video, and we will talk about this definitely more. This over here looks like I would put it maybe like right here, right? Because it never crosses. On this side, however, like I'm going to go to the same exact line, but from the top so you can see a little better. I should get a clear ruler. This one, it looks like it does cross that. And this is where I'm just going to completely throw you off until our next time working together. That is my horizontal asymptote. And I agree, it's crossing right here. And I'm going to say, what's going on? All right? Everyone say that with me. Let me get these listed first, and then we will chat. So horizontal asymptote, y equals 3. I can do this. Horizontal. Vertical, x equals -4, x equals 3. Oblique asymptote, none. And now for our little moment. What I need you guys to understand about horizontal asymptotes, and there's a note down here that we're going to write. What we need to know about horizontal asymptotes. Horizontal asymptotes basically just give end behavior. Okay? So we noticed the graph crossed the horizontal asymptote. But what I'm going to say is in the middle. Alright? It crossed it in the middle. To that I say, that's okay. And my final response is, horizontal asymptotes give end behavior, or like super far away from our center of our graph. Okay, so I want you to still know that y equals 3. If you notice, like if I continued this graph, it would come back and get really close, but it would never ever touch. Okay, so again, it can cross the horizontal asymptote, but then it's still going to approach that, just like all of our other asymptotes have done. Okay, and that is because horizontal asymptotes give the end behavior. Alright, so this video is definitely long enough, way longer than I wanted it to be. I'm sorry about that. I'm also sorry for all of my goof ups. I hope that you guys still understand what I was talking about. And I hope that this stuff is easy enough that we can work on it tomorrow in class. Have a great day.